Okay. So, generalizing this idea that f in a plane is defined with the help of two real valued function f and g. And if you look at geometrically, then you realize that this f is nothing but a continuous deformation of a piece of a line segment. So, more generally, if you consider a map from interval a b into R 3, then the deformation of the interval, continuous deformation of the interval will look like this, and this we will be calling a space curve. So, a space curve is nothing but given by a function from an interval into R 3 whose components are f t, g t and h t, okay, where f, g, h are real valued function of real variable, where f, g and h, all of them are functions from interval a b into R, real valued function of a real variable. And these f t, g t, h t, you can realize they are really the component of the vector capital F t, and usually we denote the component by x, y and z. So, we prefer to write it like this: f t equal to x t, y t and z t, okay, where x t, y t, z t are the components, where x t, y t, z t are called the components, of f t. The variable t, as I have told in the plane curve case, is called the parameter, and this representation is called the parametric representation. So, this was box 1, a plane curve, and this is box 2, the space curve. So, the representation 2 as well as 1, the representation 2 is called parametric representation. Parametric representation of a space curve. We can also write it as 3 equation x equal to x t, or equivalently we can write 2 as follows: x equal to x t, y equal to y t and z equal to z t. You may call it 2 dash. So, these are the representation of a space curve, and the t is called the parameter of the curve. Now, it is easy to note over here that you can change the parameter of a given curve. Simply you can realize it as the following. For example, I have this curve given as, say, f is a function from an interval a b into R 3, and now I can think of a map, say, from some other interval c d to a b. you know it, any two intervals in a plane in R are in fact homeomorphic. So, there is always a one-to-one correspondence from one interval to another interval. If this map is tau, then what can I do is I can compose f and tau, f composition tau, and this will be a map from an interval CD to R3. Now, the parameter t will be coming from some other interval CD. So, and still you have a continuous map from interval CD to R3, and the image will be the same graph. So, the parameter can be changed by composing these two maps. So, this is an important note, that the parameter of a given curve, the parameter of a given curve can be changed by composing it with some homeomorphism tau. Okay, this is a known fact. All right. So, now we say, this is another definition, most of the time I will consider our curves to be differentiable, in fact regular up to class Cn. So, we say that a curve is regular, we say that a curve usually we write the symbol R for a vector in a space. So, I would prefer this notation. So, and instead of writing denoting the function denoting the curve by capital F, we would write the symbol small r. Okay. So, suppose this is a given curve. So, we say that this curve is regular, curve R is regular of class Cn if this function R of t is differentiable of class Cn and the first derivative and the derivative dr over dt, which we will be denoting by r dot, is non-zero for each t in the interval a b, for each t lying in the interval a b. Now, if there is a parametric value t naught such that dr upon dt becomes 0, I will call that point t naught to be a singular point. If there exists a point t naught in a b such that r dot at t naught is 0, we say okay. We say that t naught is a singular point of the parameterization of the given parameter of the parameterization. All right, this parameterization. All right. No, no, no. If you change the parameter, sometimes the singularity is removed, and such singularities are called removable singularities. So, you have a fixed parameter, and if you get a singularity, you say it is a singularity of the parameterization. Okay. There are singularities which are not removable. Okay. Whatever parameter you choose, they insist they are always there. All right. Okay. So we have fixed up certain notation. For example, r dot stands for the derivative of r with respect to t for the curve number 1, and if you want to see its component, because the derivative of a vector valued function will be a vector, whereas for the function f the derivative was a scalar. Here you can see easily that what is the derivative. If you look at this, it is nothing but r of say t naught plus h minus r of t naught upon h limit h tends to 0. So, this is the derivative at t equal to t naught, or you can here also write down r dot t naught. So, you have seen the graph of a parametric curve. So, this is suppose the curve, and the point t naught, the image of point t naught is suppose here. This is r t naught, the vector r t naught. If you make an increment h, suppose the vector r t naught h t naught plus h is here, and the difference between them, suppose this point is p and this point is q, the difference p q is the vector, if you call it o q minus o p. Now, when you take h to be smaller and smaller, what will happen? Q will come nearer and nearer to p, and the chord will become shorter and shorter, and when q coincides with p, these chords will become the tangent vector. So, this limit if exists, we call it the derivative of this vector valued function r t. So, you can see it is a vector. So, this is a vector in R theory. And one can check the vector the components of the vector r dot t at the point t naught will be, if I consider the component over here as x t, y t and z t. Suppose these are the components of the vector r t, then r dot t naught will be nothing but x dot t naught, y dot t naught, z dot t naught. This dot always stands for the derivative with respect to the variable t. So, x dot t where x dot t naught means the derivative of x with respect to t at the point t equal to t naught. Similarly, others. Okay. Similarly, others. Yes, these derivatives are scalar quantities. When you will put them together as components of a vector, the overall quantity will be a vector in R3. Okay. Every vector. No, 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 no. This will be a vector quantity. This is,
That is the difference between two vectors actually.
yes, these two things are vectors. Their difference is a vector.
Yes,
Dividing by scalar will remain a vector. Limit of this will be a vector quantity.
I was supposing in one way it is like
No, no,
actually
no.
it is
In
difference
the
of two
case,
vectors.
yeah,
That's why it's like
yes, yes.
exactly.
All right. Okay. Now this parameter t, we usually call it a generalized parameter. There are certain things which you keep note down, because there will be other parameters that will be coming along. So the parameter t in equation 1 is known as generalized parameter. The parameter t in equation 1 is called the generalized parameter. Meter of the curve. Okay, so this is the notations that we will be having. Hmm.
So we have 4 minutes.
Oh,
Yeah, 4.5 minutes.
okay, okay. I will just complete and okay. Okay. Now, if you want to compute the modulus of the tangent vector, so modulus of the tangent vector r dot, we have already seen these quantities. So it will be square root dx upon dt. I am taking this derivative at an arbitrary point, dy upon dt whole square plus dz upon dt whole square. This will be the modulus of the vector. You know one thing, now I am trying to define as some natural parameter of a curve, parameter of a curve. We already know that if we have a curve r equal to RT, so if r equal to RT is a regular curve, then we know that its length is given by, I will denote the length by S.